Hello community! Today we talk about the latest in knowledge graph and AI. And you might say, why are you talking about a knowledge crystal? Well, I need here some specific feature, and this is a self-organizing principle. So what I want to talk today is about building an AI system that just does not process knowledge, but it can grow and organize knowledge in a particular way that suddenly it becomes a structured knowledge. And we will look here at the emergence of an intelligent pattern. So let's have a look. Now you notice, in nature we see this every time. In a cave we do have some crystalline structures growing here, some water is dripping from the ceiling and everything is great. And you know what we have? We have a complex crystalline structure, not by carefully designing every atom's position, but it just happens in nature because we have simple rules. And we have something like a self-assembly mechanism where some specific atoms just form here in a perfect, let's say, crystalline lattice. And this is what we're going to use and explore now, the same idea in knowledge. So what we have? We do have a knowledge graph, typical knowledge graph that you like, that you know. And then we say, okay, we have an AI agent. And this AI agent is reasoning on a particular topic. So given the inherent knowledge and the inherent training of this AI agent, it produces now a reasoning trace. And we transfer this reasoning trace now in a little knowledge graph, a little tiny knowledge graph only on the complex reasoning of our AI agent. And maybe there's another topic for this AI agent, so we have another sub-knowledge graph. And then we are faced with the exercise. We want to integrate those knowledge graphs, these sub-graphs here, in the main knowledge graph. So you see, we have here a crystalline knowledge structure. And we have here now an AI agent. And the AI agent is trying here to self-build, to self-assemble here more knowledge. Let the knowledge crystal grow here. But we do not give it here some specific centralized commands. We want to see this happening here, this self-assembly, this self-knowledge build up by its own. Is this possible, or are we completely on the wrong track? So we want to grow our knowledge now like a crystal, but smarter. So what we need, let's build the AI system that grows your knowledge network organically. So a kind of iterative crystallization here of the information. This is our game that we want to play today. So instead of predefining now the complete knowledge graph structure, we say, hey, we just give it here a nucleus and then we just give it here some very basic instructions so that the knowledge can self-organize in this beautiful crystalline shape of a knowledge graph. And surprisingly, it will end up looking remarkably like how human knowledge is structured. Well, of course, because we will use an AI agent that was trained on human knowledge. Now, you might say, but we know this, no? For example, this video where I showed you here multiple agents and here a graph rack system. Yes, we can build something when I give you commands, where I tell here the graph rack system here and the agent particular task. But what if I want to build a system that self-assembles over time, that continuously builds up new knowledge and integrates this knowledge here with the reasoning traces of the knowledge generation into the knowledge graph? And you see, this is what we are looking for. We will have here a beautiful knowledge graph, and you see this in this video here with a definitive agent that we have here, and we looked at Harvard and medical AI. And then we have the problem here of a large language model that has a rather transformer-like structure, no? A neural network structure. But this crystalline structure of the knowledge graph, there is a difference. And this difference, this is the real fascinating topic, because one of those networks has a characteristic the other might not have. So let's have a look at this. So now we equip here a simple AI agent with two mathematical frameworks that we need because we want to go the next step, no? We want to go to self-learning AI agent that build knowledge crystals. So what do we do? Yes, you guessed it, we go here for a mathematical category theory and a complexity theory approach, because those are the two things that we need. If you're interested why, this is my explanation. Category theory now formally structured a knowledge representation. We have there concepts like objects and relationships that are like morphism, and this is nothing else than a mapping. So this gives us here a rigorous way to represent knowledge in a more structured, in a relational format. Notice this is the relational format. It's like having a mathematical grammar for our knowledge. And then we have the complexity theory, and this deals with systems made of many interacting parts that self-organize and exhibit here some emergent behavior. Think about here a team and you're in your office, or if you are working within a team here. There's something of a self-organization that the team member find itself for a particular task. They reconfigure themselves in the team configuration to find here the optimal and stable configuration of team members. This is explained by the mathematics of complexity theory. So we will need this category theory and this complexity theory because where order arises from decentralized interaction and feedback, this is where we have our AI agent here as the crucial element. And now the combination of both of them is really what fascinates me. So we do have category theory provides here the blueprint for the structured knowledge, and the complexity theory explains how this structure can emerge dynamically and autonomously. So, interested? Let's have a look. If we say the emergence of sophisticated structured knowledge from a relative simple iterative process, this is where we have to look at, because our AI agent is a simple agent. No? Yes, it can do some reasoning, no problem, but it is just performing a simple iterative process. I get a query, this AI reasons about it, transform the reasoning pattern into a sub-knowledge graph, and then we have it. So what is our limitation? Our limitation in this moment is, of course, the complexity of the knowledge graph, but also the reasoning complexity of our AI agent. But let's say our AI agent is not that intelligent. So we have a relative simple iterative process of just adding knowledge in the reasoning form of this simple AI agent. And the fascinating thing is, in the knowledge graph, we will see an emergence of a more sophisticated, more structured knowledge. Let's have a look at this. Let's open up this video now. This was just the intro to get you interested in. So the central idea is, and we have a beautiful research paper from MIT, that a complex, intelligent-like knowledge structures, they can emerge spontaneously from relative simple iterative processes. We know this in theoretical physics, we know this here in geothermal processes, but now we do it with knowledge. So what we need, let's stick with this, we only need an iterative loop. So an AI agent reasons, adds then this reason to a knowledge graph, and then reasons again based now on this updated graph. So suddenly, we don't have only the internal reasoning of the AI agent, but it also takes now the knowledge that it just added and encoded now in the complete main knowledge graph and uses now the knowledge of the main knowledge graph for this next task. So you see we have no central multi-agent boss here in this configuration. There's no central planning AI, vision language model or large language model. This is here dictated by the overall structure. And this is why we need here specific entropy functions, but more about this later. So this arises here from the repeated local reasoning interactions from our little AI agent that just adds here some local reasoning knowledge. Okay. Now we are heading, of course, towards some autonomous knowledge discovery. And all the things that you see here for deep research from OpenAI and Google and whatever, yes, we are heading in this direction, but we're doing it in a different way, you know? We want to have some intelligence behavior from some iteration. So this particular system now shows that an intelligent-like behavior, like a knowledge organization or just generating some insights, can emerge from this iterative process without needing some explicit top-down design for the knowledge graph. Self-organization is here key. So our knowledge structure can self-organize just like any complex system in nature. Think about ants. So this shift here, the focus from some naturally grafting the knowledge base to designing system that can grow their own knowledge base organically. Again, why should we as humans code here knowledge graph? We just give it here the nucleus and a main idea how to organically grow their own knowledge. This is what we are looking for here now. Let's take here Grok 3 because it's available today. Grok 3 beta, and yeah, beautiful. And I ask it here, hey, search for, and I do this deep search or deep reasoning, or whatever you call it here. Remember, you have here the deep search and the deep thinking. So I go now here, I want a literature search. So I do go for a deep search here on Grok 3. And I say, search for category theory in the literature and provide detailed scientific explanation of the most important methods and insights we can apply category theory to scientific problems, plus explain category theory. So you see deep search goes on, 30 sources, exploring this. Those are the sources. We have Wikipedia, we have Stanford, we have again Wikipedia, and then more. So real focus on Wikipedia, because this is a trusted source of information. This is a good idea, not just to go to some internet articles or some Reddit articles that are just plain crazy. So selects the sources and comes back. And Grok 3 tells us now, hey, category theory is great for science because it simplifies complex ideas. It turns messy details into clear abstract patterns, like using functors to map one system to the other. More about functors in a minute. We connect different fields. Physics, biology, computer share similar structures. We use categories to model quantum fields or program behavior, and we can solve our problems more efficiently. Isn't this beautiful? Now, the key point, according to Grok 3, is a mathematical tool for studying structures and their relationship. This is so important that we are focusing here on the relationship between different objects, used in science to find patterns and solve problems, unify concepts across fields like physics, computer science, and biology. Key methods include functors, adjunctions, and universal constructions, making complex problems simply simpler. Useful in real-world science, beautiful. What is it? It's a branch of mathematics, looks at the big picture, how different mathematical structures relate to each other. Imagine a map that shows how numbers, shapes, or even computer programs connect. Connected here, created 20th century, beautiful. So we have objects, things like sets, groups, and spaces. Yes, set theory, yeah, group theory, Lie algebra, yes, you go there. Algebraic topology, yes, absolutely, you are on the right track. Then we have morphisms, arrows showing relationship between objects like functions or transformation. And we have rules, because morphism can be composed, linked together in a way that's associative, and every object has an identity morphism. And you exactly see here the group structure and the symmetries and so on. So, nice idea by Grok 3. Yeah, this is something I can work with. I hope you can work with this. Main methods and insight. This was the key part of my question here. Functors. They are like translators, mapping one category to another while keeping the structure. Okay, that's an interesting view. Help compare different scientific models like linking physics theory. Well, yeah, okay. Adjunction, show dual relationship like free groups relate to groups. Understanding of symmetry in physics, yep. Universal constructions, biology, system modeling, equivalence, higher category theory, quantum field, yeah, there's quite some other mathematics. So, okay. So now comes the spark. You know, in these videos, we already have a spark here, a little bit genius. And this is this paper by MIT. Now, normally I don't show you papers where we have only a single author. But I know this author, I've seen the work of this author for now multiple years. I read the study, it's more than 100 pages. This is really an unusual study. Just want to make this clear right from the beginning. Published February 19, 2025, MIT. We are here, Center for Computational Science and Engineering. And it is about agentic deep graph reasoning that it yields here a self-organizing knowledge network. And there's a lot of experiments, especially here with material science here. And I just look at the keywords like graph theory, category theory, material science, language modeling, reasoning, isomorphisms, and engineering. So these 100 pages are great. I just look at a very tiny element of this. I want to look at here the dynamics of my knowledge crystal that's self-forming. So I just have a structure knowledge graph and an AI agent Can this build the world? Now, Markus tells us here, hey, we present here an agentic autonomous graph expansion network that iteratively structures and refines knowledge in situ in the knowledge graph. And unlike conventional graph construction method that rely on static extraction and single pass learning, they have here exactly the couple here, the reasoning native LLM, our AI agent, with a continually updated graph representation. So this is exactly what I showed you here, also a topic that I'm currently thinking about, a knowledge graph AI agent, add knowledge. Now, please remember, an agent is defined in itself that it has a context to the external environment. The agent is not that it is isolated, but with function calling or whatever we have direct interaction. It interacts here per definition of an AI agent with the environment. Therefore, the environment is something where this agent can see new facts, can see new structures emerging, can detect new objects, and maybe come up here with a reasoning path for unseen objects with unseen reasoning traces. So here, the feed in of this new data, of this new relationship, especially from category theory, our AI agent should be able to learn. So this means there's a certain minimum threshold in the complexity of this AI agent that this AI agent has to have to be able to deduct further data from the environment and understand the reasoning process. Okay, you see, it's easy. If you want to see my video, this is already months old, that I did on swarm intelligence, very simple multi-agent ecosystem. How does AI swarm intelligence build? How does it grow? Just an example of nature. Look at this. This is absolutely amazing. So let's come to the core idea of this video. According to this MIT study by Markus, we have an agentic system. No, it's not passive. It actively participates in the knowledge construction itself. It modifies here the knowledge representation based on its own evolving understanding as an AI agent. So we do have a real dense interaction between our knowledge graph and our AI agent. Plus, we have now a graph as the native knowledge representation. Careful, you might think, yeah, but we also have a knowledge representation within our AI agent. Yeah, but this is exactly the topic of this video. Now we have two entities. We have a dynamic knowledge graph and a little AI agent that is also intelligent, but now feeds iteratively pieces of more information, of more relation, of new unseen objects into this knowledge graph, into this knowledge crystal that grows now with time. And this is crucial. Graphs are inherently relational, allowing here for the explicit encoding of concepts and their relationships. So now the most important sentence, this structure enables the system to capture higher order patterns like hubs or bridges or communities in the graph structure, which are often implicit in the text or other unstructured data. So now we have an emergence, but not this super intelligent, just that in a graph we see suddenly higher order patterns emerge here when we look at the graph structure. We see hubs, bridges, and communities, clusters emerging. Now, this is nothing special for the graph. Special is that higher order patterns emerge by an iterative process that maybe is less intelligent. And now to the main question. Can a neural network, can a transformer-based AI agent self-develop higher order knowledge patterns as an agent? Or is the agent not able? Is the agent the wrong object to do higher order knowledge? The agent is just feeding in iterative processes here, and here we have the emergence of higher order patterns, given that we have here these specific two mathematical models that we work and we integrate here. This is our crystalline structure here of the knowledge. So where is the complexity now? We can reformulate this. If an AI agent can self-train itself on a higher complexity input from the environment, so it sees new data, higher complexities are there, we generate now, we see this, we notice it, we want to generate data sets, and we want to self-train an agent. We know that an agent with a higher complexity data set, if we train this, the agent will perform this higher complexity task. But the point is, can an agent with its given intelligence detect higher complexity in the environment? Or is it limited inherently by its maximum complexity knowledge that it can detect, analyze, and understand? This is something that is not as easy as you might think. Because can an AI agent really detect higher complexity in the real world, in the environment? Or will it be limited to its own complexity, its inherent complexity level? And then there's the other question. If we say no, it cannot detect this. So it takes here its little sub-knowledge graphs, it puts in here, but here now in the graph, higher order patterns emerge. And you remember I told you that for the next task, the little AI agent now takes the complexity, takes everything here of this new knowledge graph, including higher order patterns, as a base for the next decision. So we have maybe a limited internal complexity structure, but with the graph we have access to a higher order pattern. Is this now enough for our little AI agent to reason on the next complexity level? Although it is not an inherent knowledge of the AI agent. So can this AI agent detect higher complexity in the graph? And if it can detect it in a graph, then it should theoretically be able to detect it in a real environment. Or are there mathematical limitations that we have to be careful of? Now we are talking here about self-organizing knowledge networks. And you remember the structure in our crystalline structures emerge here from the feedback loop itself, from this little iteration. Think about here the complex systems in nature like ant colonies. So self-organization into functional units without central control is something that we know. But again, since we have no design top-down approach, does it have natural thresholds that it cannot cross given a certain complexity level in the reasoning process? I mean, we humans can detect higher order structure in a graph. We see it. We see that new objects emerge. But can an AI agent realize and detect it and use it? So the question is, can an AI agent extract higher complexity patterns from a graph and design higher complexity training data sets for the same AI agent to self-train itself for a higher complexity level? Or is the AI agent simply unaware that it is extracting a higher complexity pattern from a graph because there they exist and he built it, this little agent, and thereby now designing artificial higher complexity training dataset, although not realizing about a complexity threshold, it can self-train itself now on a higher complexity level? I find these questions interesting. I'm currently running some tests on this, but you see, this is where AI research is currently heading, and I love this article by MIT. Okay, let's come to the facts. The main hypothesis was the following for the MIT paper, and I'm referring now to the MIT paper. A recursive graph expansion is our topic. And this recursive graph expansion by our little AI agent, limited or not, enables now some self-organizing knowledge formation, leading here to an intelligence-like quotation mark behavior without predefined ontologies, external supervision, or centralized control. Now, the process schema is rather simple, yeah? We generate some graph-native reasoning tokens. We have here an LLM. MIT went here with a specific LLM, where I have here a reasoning token with beginning of thinking and end of thinking. You notice this is classical. So this explicitly marks here the model reasoning process, making it here extractable, interpretable. We can compute further on this. From the LLM's reasoning token, a local graph, G local, is now extracted, built. Simple, we know this. Involves identifying concepts in the node and the relationships in the edges. So we have now transformed some unstructured textual reasoning into a structured graph format. And then we merge the extracted graph with the larger graph. You know how to do this, no problem. And then comes now this interesting part. Yeah? We generate now a new question. So based on the newly added nodes and edges in our local graph, a new follow-up question is now generated. And this is now the crucial feedback mechanism. So the system uses now its own recently acquired knowledge that it put in the graph to guide its next step of exploration, ensuring here an iterative refinement and preventing here some aimless wandering around in an empty space. So this system now is more intelligent because it doesn't wait here for a new prompt by the user for the next more complex task, but the system now generates its own question. So it's designed to have a feedback mechanism where it rechecks now, hey, do I really understood this acquired knowledge now that I extract now from the graph? And this is such a beautiful idea. And then we have an iterative reasoning in the loop. It goes on and on and on. And this more or less is our engine of the self-organization, allowing here our main graph to grow and evolve dynamically by the knowledge fed in by our little AI agents. And there are hundreds of questions that remain, of course, because remember, we are talking here about the growth potential if we go to higher complexity levels of a knowledge graph structure as a network and of a neural network. So what are the differences? What are the growth trajectory regarding here a complexity evolution? Absolutely fascinating. Okay, let's come to an end. So this study also provides more than 100 pages. Have a look yourself. It is a really fascinating. It gives you so many brand new ideas, but they also have some, let's call it experimental data. And content is, we have some scale-free network structure that emerge. So from all the tests that they did, they exhibit some scale-free characteristics. So this means that the agreed distribution follows here power law, indicating the presence of few highly connected hub concepts. This structure we know common in real-world networks, including our knowledge, our social networks, our biological networks, beautiful. But this means now that this suggests that our system naturally organizes now knowledge hierarchically, with a central hub acting here as organizing principle, mirroring here kind of a human knowledge organization. Plus, we have bridge nodes. Graph here exhibits here the emergence of highly connected hub nodes and the bridge node connecting disparate knowledge clusters. So the hubs represent here the core concepts around which knowledge clusters, while the bridge node facilitate here, if you want, an interdisciplinary connection and kind of a knowledge synthesis. So it builds here the bigger picture. Plus, we have modularity, small world properties. We have distinct conceptual communities emerging, community formation. Yeah, beautiful. We have linear growth. We have a non-saturation. Interestingly, even if we go to thousands of iterations, this shows us here more the open-ended nature of this knowledge expansion process in the knowledge graph itself. The system seems to continue to learn and learn and learn, integrate continuously new information without becoming redundant or collapsing under its own complexity. Of course, here we depend here on the reasoning capability of our AI agent. So you should not go with an agent that is maybe not there in its intelligent level yet. We do have a dynamic evolution of the network properties. You should have a look here at modularity, shortest path length, diameter. You have all the neural network centrality figures, beautiful. And the interpretation is the system undergoes phases of structural reorganization of the knowledge, which is amazing in itself, suggesting here that a self-regulating process that leads to a stable and a more efficient knowledge structure. This is something, yeah? Especially when you read the next one, that there are sudden breakthroughs with new concepts. So there seems to be that the system becomes more and more and more, a little bit more unstable, a little bit more unstable, the more we add mass to this logical concept, this knowledge graph. And then suddenly it finds a new configuration that is more stable. So the knowledge, if you want, reconfigures itself and builds a hybrid knowledge expansion model. It is not that easy to explain on a pure knowledge level, but hey, this more optimal configuration of knowledge complexity, it seems that they might exist. This is all I can tell you for the moment. Just remember the complexity level is one of the most important factors. In this video about LLMs and their breaking points, we looked at some beautiful exploration, and we had here the complexity of a task. And we had a small complexity, medium, larger models, and X-large models. And we have here these reasoning models, O1 and O3, and DeepSeek R1, and the non-reasoning models like GPT-4o or Claude Sonnet 3.5. And you see the moment we go up in the complexity, you see the non-reasoning models, the performance goes to 0. And even if we look at a large model, and this is a 6x3 matrix complexity, if you want, have a look at my video if you want to know more, you see even here the O1 mini comes really down, and only the R1 and the O1 have here the performance. And then if we just go from 6x3 to 6x6 in a matrix structure, you see even the biggest model here fail to solve this. So the level of complexity, if it increases, would a little AI agent be able to build a knowledge graph that would inherently form stable configuration of new reasoning traces that are able to solve higher complexity tasks? I think it's an absolute fascinating question, and I don't have an answer. So if you have an answer, please leave here a comment. Let's look at a work by MIT, and you will see, or I feel that there's a certain limitation to it, you know? Like, let's have a look here at this image, and you see we're building up complex ideas from simpler components in a hierarchical and interpretable manner. So we have here atomic concepts, then we have pairwise compositional fusion of those, and then we have bridge synergies, and then we have the final discovery. Now, it's simplified, but you get the idea. So we have here, I don't know, materials for infrastructure design or biodegradable macroplastic. And then suddenly the pairwise fusion is eco-resilient infrastructure design. I'm not sure that, you see, the question is, let me reformulate it. The question is this here a low complexity? Is this here a higher complexity? Or are those not complexities that are more or less in the same level, in the same group, in the same set of complexities? Because I have a feeling that there's not a jump over the borders of a complexity into a new set of higher complexities. I think this is more or less on the same complexity level. And now the question is this complexity level determined by the complexity capabilities of our AI agent? Or is it somewhere in between the AI agent and the emerging features on the knowledge graph? I can't give you here even a feeling from my side because I don't know it. The interpretation here highlights here the system's capacity for systematic and logically sound knowledge construction, going beyond simple pattern recognition. And I absolutely agree. This goes beyond simple pattern recognition, but we are talking here about more complex tasks and here complexity levels. So no way it goes beyond pattern recognition, but does it really cross a complexity border? I'm not sure about this. Yeah, let's come to the summary. We have something beautifully. We have a recursive graph expansion in this paper of the MIT as a model for self-organizing knowledge. And this knowledge itself can self-organize and grow organically if you just put here an AI agent with a contact to an external real-world environment where the agent can learn, can view new things, new objects, learn new relations, self-train itself and build a knowledge graph. Second, compositional reasoning for systematic knowledge synthesis. So building up these complex knowledge ideas from simpler components as provided by our AI agent, the graph can do this and address here limitations of the LLM in its own limited systematic reasoning, because it seems to be that the knowledge graph can represent higher complexities easier than a neural network or a transform architecture. And this beautifully aligns here with the growing field that we see with AI-driven scientific discovery in medicine, in mathematics, in physics, in material science, in space science, wherever you go. Those efforts to automate here hypothesis generation and knowledge synthesis in science and engineering. So this is fascinating, especially if you think about space and so on. So this could theoretically offer you a novel approach to self-organizing and emergent knowledge, rather than just the classical AI of data analysis and pattern recognition. So maybe you understand now why I'm kind of excited about this new idea, because I think this is the way for AI to go. And there are so many open questions. I don't have even an idea how to start to answer this. Well, maybe I have an idea, but more about this in a later video. And what I wanted to show you just yesterday, February 19, 2025, Google researched a new publication accelerating scientific breakthroughs with an AI co-scientist. So Google tells us here, hey, we developed a new multi-agent AI system with, of course, Gemini 2.0, hopefully, as a virtual scientific collaborator to help human scientists generate new hypotheses and research proposals, especially also then for biomedical discoveries. So I think this might be the context of my next video, because I will have a look at this. I will have to read it in another time. And then if I decide that this is kind of a follow-up video, yeah, you will see it as a subscriber right here on this beautiful channel.